Part 5, even and odd functions. Let's first define symmetry. 2 points A, B, and C, D in the plane are said to be symmetric about the x-axis if A equals C and B equals negative D. Looking at the figure on the left, I can see 2 points A, B, and C, D that are reflected about the x-axis. So those 2 points are symmetric about the x-axis. And in fact, that entire ellipse is symmetric about the x-axis. Looking at the middle figure, I see that we have 2 points A, B, and C, D that are symmetric about the y-axis because A equals negative C and B equals D. The figure on the right shows 2 points that are symmetric about the origin. A equals negative C and B equals negative D. Notice if they are symmetric about the origin, we can think of that as the points being rotated 180 degrees, and then they will match back up. So if I rotate this figure 180 degrees, CD will be where AB is, and AB will be where CD is. To test for symmetry about the x-axis, we will replace y in the equation with negative y. To test with respect to the y-axis, we replace x with negative x. And to test for symmetry about the origin, we replace x with negative x and y with negative y. And then if we can simplify and the resulting equation is equivalent to the original equation, the specified symmetry exists. Let's do this for y equals cube root of x. We'll first test for symmetry about the x-axis. So I'm going to replace the y with negative y. And then if there is something I can do to simplify this and somehow make this look like the original function, then it would be symmetric about the x-axis. But I could not. I could multiply both sides by negative 1, but that would just move the negative. It would still be there. So it's not symmetric about the x-axis. Next, I will test for symmetry about the y-axis. So in my equation, I will replace the x with negative x. And noticing this, if I have a negative inside an odd root, I can put the negative in front here. So now I have y equals negative cube root of x. And again, I cannot get rid of that negative and make it look like the original equation. So we are not symmetric about the y-axis. If I test for symmetry about the origin, I'm going to replace both the x and the y with their negatives. And now I have negative y equals negative cube root of x. And again, I can bring that negative outside of the odd root. And then if I multiply or divide both sides by negative 1, I end up with y equals cube root of x. And this is the original function that we started with. So it is symmetric about the origin. Let's do the same thing for this function. Let's test this for symmetry. So first I'm going to test for symmetry about the x-axis. So we will replace the f of x with y. And then if I make y equal negative y, I'll have negative y equals x squared plus 2 over 3x. For this function, if I could multiply or divide by negative 1, I'm still going to have a negative that's not going to go away. It's not going to look like the first equation, so it's not symmetric about the x-axis. To test for symmetry about the y-axis, I'm going to replace the x with negative x. So if I do this, the negative x squared becomes x squared. So that part simplified to the original equation. But my denominator now is negative 3x. And that part we cannot simplify to the original equation. So it is not symmetric about the y-axis. And then to test for symmetry about the origin, I will replace y with negative y and x with negative x. So I could rewrite this now as x squared plus 2 over negative 3x. And now if I multiply both sides by negative 1, I would get y equals x squared plus 2 over 3x, which is the same as the original equation. So yes, this graph would be symmetric about the origin. Even and odd functions. A function is called even if its graph is symmetric about the y-axis, and odd if it's symmetric about the origin. Notice we don't have a word for a function that is symmetric about the x-axis because if a graph is symmetric about the x-axis, it is not a function. This graph represents an even function because it is symmetric about the y-axis. The whole graph is reflected about that y-axis. This graph represents an odd function because it is symmetric about the origin. If I rotated this graph 180 degrees, it would be back onto itself and look exactly like it does now. Testing a function for symmetry. The graph of a function f is symmetric about the y-axis if and only if f of negative x equals f of x for all x in the domain. This was what makes a function even, if it's symmetric about the y-axis. So if f of negative x equals f of x, we have an even function. And the second one, the graph is symmetric about the origin if and only if f of negative x equals negative f of x. And this is what makes a function odd. If we have a function that's symmetric about the origin, it's odd. So let's think, without looking at the graph of this function, determine analytically if the function is even, odd, or neither. To do that, the first thing we're going to find is f of negative x. So I'm going to replace all of the x's in the function with negative x. So I have 3 times negative x squared minus 4. Now that negative is inside the parentheses, so when I square negative x times negative x is x squared. So I get 3x squared minus 4. This is f of negative x. Then I look, is this the same as f of x? In this case, it is. Both f of x and f of negative x are 3x squared minus 4. So f of negative x equals f of x, which is what this first statement says. So this graph, this function, is even. If I were to draw the graph, it would look something like it's a parabola where we go down to negative 4, and it actually ends up looking something like that. And we can see it is symmetric about that y-axis. If my graph had been drawn better, you would be able to see that better, but it is symmetric about the y-axis. Let's try this next function, 7x plus 2. So we're going to find first g of negative x the same way we started before. So I have 7 times negative x plus 2, which is negative 7x plus 2. This does not equal g of x, which means this function is not even. Then, if it's not even, I will try negative g of x. So negative g of x is negative 7x plus 2. And distributing that negative through, I get negative 7x minus 2. That is not equal to g of negative x. These two are not equal, so this is not odd. That means this function is neither even or odd. Determine analytically if the function is even, odd, or neither. We still start with finding h of negative x, which is 2 times negative x cubed minus negative x. Simplifying that, I get negative 2x cubed plus x. This is not equal to h of x, so the function is not even. Next, I find negative h of x, which is negative 2x cubed minus x. Distributing that negative through, I get negative 2x cubed plus x. Notice this is equal to h of negative x. These two are exactly the same, so this function is odd.